Hi, so in this video, I want to go over some of the mathematical tricks that we'll sometimes use when working through ice table problems. There are certain ways that we can use math to help us out, right? Definitely make a problem easier. There are also ways sometimes that the math is just complicated, and I acknowledge that, but there are still ways to solve those problems. So I want to take a look at some different methods that we can use to, again, just kind of help when solving a whole variety of different styles of ice tables. So let's begin by looking at this reaction right here. So I have 2 moles of nitrogen dioxide forming 1 mole of dinitrogen tetroxide. This has an equilibrium constant of concentrations as 4.7. And let's say initially we have a vessel that is containing just N2O4, and it's initially 1.00 molar in N2O4. So my question following this up is, what is the concentration of nitrogen dioxide at equilibrium? So again here, just pause, take a couple minutes to set this up, think how you would work through this problem. Again, we're going to need to use an ice table here because we have some initial concentration. We want to know the equilibrium concentration. But so pause, take some time to think how you might work through this. And if you get stuck or anything, then you can unpause, but hopefully you should be able to maybe mathematically work this one out. All right, so working through this one, I found that the equilibrium concentration of NO2, again, if we're starting with just 1 molar of N2O4, my equilibrium concentration is found to be 0.411 molar. So you may be thinking, how the heck am I supposed to do this? Again, what we're going to kind of do is just set up an ice table, and then we're going to see maybe how, again, the math may be a little weird, but hopefully we can work through it. So here, let's begin by just setting up an ice table. You guys know the drill. I have my reaction written out. I have ICE for my different rows. And so initially here, my concentration of just N2O4 is 1.00 molar. That implies then, because NO2 is not mentioned, right, that we've got 0 molar of the NO2 to begin. And so there's my initial line. The change is, of course, going to shift towards the NO2. So we're going to add to that 0. Specifically though, because pay attention to the molar coefficients here, NO2 has 2 as its molar coefficient, so we're going to add 2 equivalents of change, or 2x, to the NO2 column. For the N2O4, it's just going to be losing x, so we'll say minus x as the change for N2O4. Again, pay attention to our molar coefficients and which way the change is being added. Right, in this case, we're adding to the reactants because we didn't have any reactant to begin. And so in my final line here, I can show the equilibrium concentrations of each of my reactants and products. For the NO2, we have 2x, and then for the N2O4, we have 1.00 minus x as its equilibrium concentration. Again, I'm going to solve for x just using my equilibrium constant and the Kc expression that goes with it. So in this case, our equilibrium constant is 4.7. That's equal to the concentration of N2O4 divided by the concentration of NO2 squared. So right, thinking back to that mass action expression, or the ratio of products over reactants, each of those are taken to their molar coefficient power, and so that's kind of how I've set things up here. Now there is a decent amount of math in this portion of 163, so we're just going to work through the algebra right here. I'll start solving, kind of combining different things together, and so my work is shown in each of these steps here. Pay attention and be careful, especially whenever we have, say, a squared concentration or a cubed concentration. Oftentimes, the concentration itself is going to have not just x in there, but 2x or 3x or whatever. So in this case, we've got 2x, that's the concentration. That whole thing is squared. And so when we square that, right, we want to make sure that we're squaring not just the x itself, but we're squaring the number in front of x as well. So that's why here I've shown this step where my denominator goes from 2x squared to 4x squared, right? Because both the 2 and the x were squared there, I now have 4x squared as the denominator. I know it sounds silly, I know you've taken math classes, but these are things that people often forget and they just kind of miss sometimes when they're working through the math very quickly, right? Don't forget to square the entire thing that's in parentheses there when working through these types of problems. All right, so carrying on then, I can again kind of start putting things together, combining like terms, and oh shoot, I realize that I am looking at a polynomial, right? I have an x squared term, I have an x term. There's no way for me to like cancel that out or anything. Whenever we have like a variable that's shown to different powers, it can be a little trickier to solve for that variable. In our previous examples, we've just been looking at like just a single x. There's no squares to it, or if there was squares, they got factored out earlier on. And so now I'm a little bit like nervous about how I'm going to solve this algebraically. But keep in mind, right, that we do have ways to work with polynomials like this one. For this, we're going to use the quadratic formula. So just as a reminder, the quadratic formula works to help solve for our variable x when it appears in a quadratic function. So a quadratic has both x squared terms, it has x terms, and so to solve for x, we're going to use this equation to do so. Now, in order to use this, right, I'm going to need to rearrange my existing equation to match the following format, where I have all of my x squareds, all of my x's, and all of my non-x stuff pushed all to one side of the equation so that the other side of the equation is just equal to 0. So I'll go ahead and rearrange what I've got so far to do that. That looks to me like 18.8 x squared plus x minus 1. That is all equal to 0. Now, when it's in this format, each of our different say pieces of that left side of the equation, they have their own coefficients. These coefficients we'll refer to as a, b, or c. For the coefficient in front of x squared, right, that's the a coefficient, or the coefficient in front of x is b. So in this case, my a is 18.8, b is just 1, and then c is going to be -1. So right, when we organize our quadratic in this way, we can kind of define then all of these a, b, c terms. This is helpful because when we actually use the quadratic formula, which I have written in the box right here, right, this solves for x based off of all of those different coefficients. So the formula reads as follows, as x is equal to -b plus or minus, and then this whole thing is in a square root, b squared minus 4ac. Then I take all of that and I divide that by 2a, right? That should solve for x. So setting that up right here, again, with my a, b, and c that I defined just previously, right? I have basically this big, long equation. Now note that because this equation includes a plus or minus to it, we're basically going to get two answers out from this, right? When I solve this, I can solve it for the plus side of things, I can solve it for the minus side of things, and so I get then two answers here, either 0.206 or -0.259. Now to know exactly which x I'm supposed to use then, which is my actual answer here, right, keep in mind just like how concentration works, how you can't have a negative concentration at any time. And so what we're going to do is choose the x value that when it goes back into our ICE table, it only gives us positive values for our products and reactants. If, for example, I said that x was that -0.259, because the concentration of NO2 at equilibrium is 2x, that would be some negative concentration then for NO2. We can't have that, right? It doesn't make sense to have a negative concentration or a negative mass or a negative pressure, right? Those are all things that are always going to be positive. And so while solving for x gives us two answers, the true x answer that I'm going to have here is just that 0.206, right? That is our actual x value. And so when we plug 0.206 into our ICE table again, we get then the following concentrations at equilibrium: 0.411 for the NO2 and 0.794 for the N2O4. Now, just as an aside here, when we solve for the quadratic formula, if we've set up everything correctly in our ICE table, we only need to solve it for the plus side of things. So when we say -b plus or minus, right, you can really just solve it for the plus. You don't need to solve the minus, again, if you've set up your ICE table correctly. What I mean by correctly there is if we've chosen the correct side for our reaction to shift to, That is, if we've defined the correct positive change to the reactants in this case. Now in this example, it's kind of hard to mess up which way the reaction is going to shift because again, when we start with 0 initially, it's very easy to decide, okay, that needs to be added to. But if we have other examples where we're maybe starting with both products and reactants, deciding the shift of the reaction, whether we add to the reactants or whether we add to the products, that step is really crucial, especially when trying to take maybe little shortcuts like this one. So if you're really confident in how you've set up your ICE table, then solving for x just by using the plus of the quadratic formula equation will work. But if your ICE table was not set up correctly, then you may need to solve for both x's and actually think through the whole thing. But so I just point that out there because again, I do want to save you guys time. I don't want you to spend necessarily all of your time just doing math when there's chemistry to be learned as well. But this is just a little hint here. If we set up our ICE table correctly, then we only need to solve for one way of the quadratic formula. All right, so this is again one of the ways in which our ICE tables can get a little bit more complicated just in terms of math, right? If we do have some kind of polynomial like this one, we can use the quadratic formula to kind of help solve for that, right? And determine x maybe through some more complicated algebraic means than some of our other examples. Now on the flip side, actually, I want to show you a math trick that we can use that actually makes the calculations easier. So for this, let's take a look at another ICE table. This time the reaction of cyanide and water producing hydrocyanic acid and hydroxide ions. This has an equilibrium constant of 1.6 times 10 to the minus 5. So let's say I prepare a solution of 100 grams of sodium cyanide into 500 milliliters of water, or into, let's just say 500 milliliters total of solution there. What would be then the concentration of hydroxide once this reaction has reached equilibrium? So you know how this works, right? Go ahead and set up an ICE table, solve for our concentration of OH minus at the end of this reaction, and then we'll discuss it in just a moment. All right, so working through this one, there is an additional step, which I haven't shown you necessarily in previous examples, but it is stuff that you should be able to do. But hopefully with all of that even, you should be able to find then the answer here as 8.1 times 10 to the minus 3 molar as our final concentration of OH minus. Now, if you did not get this answer, let's go ahead and look through the math on it. Even if you did get the answer, I do want to show you a little trick that we can use, a way to maybe speed up the process in solving a question like this one. So again, I'm going to start with my ICE table. Here I have my reaction. My initial concentration of cyanide I calculated as 4.08 molar. This is the step that I didn't show you guys previously because this is just determining the concentration of the solution based off of these grams and milliliters amounts that we're initially given. So the process here would be simply taking my 100 grams of sodium cyanide, using the molar mass to convert that into moles. We know that the sodium cyanide itself is going to dissociate, right? Remember that that's the process of an ionic compound or an acid separating into its individual ions. For sodium cyanide, when it dissociates, it produces 1 mole of cyanide to every 1 mole of NaCN. And so whatever our moles of the sodium cyanide were, that's our moles of cyanide as well. We can then divide that by the volume, of course, in units of liters, to give us then our moles per liter or our molarity concentration for the cyanide. Again, I didn't show that because that's 161 stuff, y'all know that. But if you do want to review molarity concentrations and things, then I'm happy to go over that with you in my office or whatever. But so right here, I set up my initial concentrations. Of course, I have just the cyanide to start, none of the HCN and none of the OH minus. And also in my ICE table, I include water as just one of the reactants, but I'm not actually going to keep track of its concentration. There's no real concentration to water. It's not a solute, it is the solvent. But also remember that pure liquids and pure solids don't play a role at all in the equilibrium constant. And so I don't need to keep track of its concentration because it's not going to matter to me mathematically later when I plug everything back into the Kc expression. But so my initial line reads like so. then the change is, of course, going to be adding to the products, subtracting from the reactants, and all of these have a molar coefficient of 1, so we'll just write minus X for Cn minus, and then plus X for HCN and for OH minus. That means then that at equilibrium, my concentrations are 4.08 minus X for the cyanide, X for HCN, and then X for hydroxide. So of course from here I can then solve for X using my equilibrium constant. The equilibrium constant expression I've written out as again like the concentration of the products divided by the concentrations of the reactants. So that looks like HCN times OH minus divided by Cn minus. Or putting in my actual like equilibrium concentrations, I would take each of the concentrations from that equilibrium line and just plug that into the expression. Except, as I promised, there is a trick that we can use that's actually really helpful for us. So, let's think about kind of how this reaction is supposed to look once it reaches equilibrium and how that compares to it right now. So our equilibrium constant, 1.6 times 10 to the minus 5, that hugely favors the reactants, right? When you have a super duper small K constant, you expect very little products to form and mostly just have reactants at the end of this reaction. And if we look at our initial amount of our reactant, the Cn minus, we see that we already have like quite a bit of it, right? We have 4.08 molar. That's like a really high concentration, honestly, of a solution. And so with that 4.08 molar, because again, the reactants are favored in this, I don't really expect that 4.08 to change much. So it kind of goes as a general rule that if our initial concentration of a chemical is greater than the equilibrium constant times 1000, then whatever change is going to happen to that initial concentration, it's going to be very minimal. It's going to be negligible, basically non-existent in terms of how big our initial concentration is. So we make this determination off of every single chemical in the reaction, right? Individually, we look at its initial concentration and how it compares to the K constant itself. In this case, for the cyanide, because it is greater than 1000 times Kc, right, we can essentially just ignore whatever change happens to the cyanide. And so we can say effectively that the concentration at equilibrium for Cn minus, that's just going to still stay at 4.08, right? So although there is that minus X in there, that minus X is relatively small, and so it can be basically ignored from this portion of the concentration. Now that said, for HCN and for OH minus, those initial concentrations were 0, so obviously not more than 1000 times the Kc, and so the change that occurs to both of those guys, that does still need to be counted and considered, and so we still express their equilibrium concentration as X, which is then what we can use to solve in our K expression. My math is going to look a little bit more simplified, as you can see down here, right? Basically, I have X squared divided by 4.08. That's equal to 1.6 times 10 to the minus 5. And so I can work through this mathematically, say that X squared is equal to 6.53 times 10 to the minus 5, and then taking the square root of both sides, X is equal to 0.0081, right, or 8.1 times 10 to the minus 3 molar. Again, if we kind of think through how minuscule this X is and how very little it's going to change any of our cyanide concentration, right? If we start with 4.08 molar of the cyanide and we subtract out from this 0.0081, it's still basically going to be 4.08, maybe like 4.07 if we're rounding, but right, this is very tiny change to the cyanide because we started off with so much of it. For the HCN and the OH minus, however, those are going to have now this new concentration of 0.0081, And so we still can calculate X and plug it back into our ice table, but right, just in terms of how much it changes our different products and reactants, it may be negligible in some cases, again, if we start with a lot of one thing. But so again, these are like some more just kind of like mathematical tricks and steps that we can use when approaching ice table problems. We'll see a lot of different ice tables throughout the quarter, so please let me know if you have any questions, and I'm always happy to help. Bye.